2 billion light-years away, a massive star died. Its core collapsed into a black hole, and for 10 seconds, it emitted a beam of gamma rays aimed almost directly at Earth. On October 9th, 2022, that beam arrived. Satellites failed. The ionosphere rippled. Astronomers called it the boat, the brightest gamma ray burst ever recorded. We survived because of distance. 2 billion light-years was enough. But if that star had been in our galaxy, 6,000 light-years away, you wouldn't be watching this. Earth's ozone layer strips away in seconds. UV radiation sterilizes the surface. Forests die, crops fail, ecosystems collapse. Civilization, if it survives at all, retreats underground. And the biosphere takes millions of years to recover. This isn't science fiction. It's happened before. 445 million years ago, 85% of marine species went extinct in a pattern consistent with gamma-ray sterilization. And statistically, we're overdue for another. You exist because the universe keeps missing. 1 degree of misalignment saved us last time. But gamma rays travel at light speed. There's no warning. By the time you see it, it's over. Your existence is a cosmic lottery, and the odds are not in your favor. Before we dive in, please consider subscribing and liking this video. Your support truly helps us continue this work. Thank you. The story begins not with a gamma ray burst, but with something more familiar, something that actually did hit us 66 million years ago. If you were standing in what would one day become the Yucatan Peninsula on that particular morning, you would have had approximately 1 second to appreciate the beauty of the Caribbean before the sky caught fire. At 13:16 and 32 seconds, give or take, an asteroid roughly 10 to 15 kilometers in diameter, traveling at 20 to 30 kilometers per second, struck the Earth at an angle of approximately 60 degrees from horizontal. To put that speed in perspective, the fastest human-made object, the Parker Solar Probe, tops out at about 190 kilometers per second at its closest approach to the Sun. This asteroid was moving at roughly 1/6 that velocity, which doesn't sound impressive until you remember that it had a mass of somewhere between 1 and 4 trillion kilograms. A mountain moving at 70,000 miles per hour. The impact released energy equivalent to roughly 100 million megatons of TNT. That's more than 1 billion Hiroshima bombs detonating simultaneously. The explosion vaporized the asteroid, the ocean beneath it, and several kilometers of crust. It triggered a magnitude 11 earthquake, something we have no modern reference for, that made the Earth ring like a bell. Seismic waves propagated through the entire planet. On the opposite side of the world, in what is now India, the Deccan Traps, already in the middle of one of the largest volcanic eruptions in Earth's history, intensified as the shock wave destabilized magma chambers. At the impact site, rock was compressed so violently that it momentarily behaved like a fluid. The crust rebounded, forming a transient crater 20 kilometers deep and over 180 kilometers wide. Mountains higher than the Himalayas ringed the crater for a few minutes before collapsing back into the pit. Molten ejecta, rock heated to thousands of degrees, was flung into space. Some of it achieved escape velocity and left Earth entirely. Most of it fell back, re-entering the atmosphere as millions of fireballs that ignited forests across the globe. But the immediate destruction, as apocalyptic as it was, wasn't the main event. The main event was what came after. The impact ejected so much vaporized rock, sulfur compounds, and soot into the stratosphere that within hours the sky darkened. Within days, a global haze blocked sunlight across the planet. Temperatures plummeted. In the tropics, where temperatures might normally hover around 30 degrees Celsius, they dropped to 5. In higher latitudes, everything froze. This wasn't a brief, cold snap. Computer models suggest the impact winter lasted at least 15 years. Some estimates push it to several decades before enough particulates settled out of the atmosphere for sunlight to meaningfully return. And without sunlight, photosynthesis stopped. Not slowed, stopped. Plants died. Not all of them, not everywhere, but enough. Seeds and spores could wait it out. Mature forests could not. Herbivores, deprived of food, starved. Carnivores deprived of herbivores followed. The food chain collapsed from the bottom up. 76% of all species went extinct. Every single non-avian dinosaur, every pterosaur, every large marine reptile, the coiled ammonites that had dominated the oceans for 300 million years. Gone. On land, no animal heavier than about 25 kilograms survived. The largest terrestrial survivors were small omnivores. Mammals, yes. But also birds, lizards, crocodilians. Anything that could scavenge, burrow, or otherwise wait out the darkness, eating whatever organic matter remained. And when the dust finally settled, when the skies cleared and warmth returned, it wasn't a return to the status quo. It was a completely different world. Here's what's remarkable about the Chicxulub impact. Not that it happened. Asteroids hit planets. That's normal cosmic weather. What's remarkable is the angle. 60 degrees from horizontal. Recent research published in the 2020s modeled what would have occurred if the asteroid had struck at different angles. If it had come straight down, perpendicular to the surface, the energy would have been more concentrated locally. Devastating to the immediate region, catastrophic to the hemisphere, but not globally apocalyptic. Much of the ejecta would have fallen back nearby rather than being flung into the stratosphere to spread worldwide. If it had come in at a much shallower angle, grazing the atmosphere, it might have skipped like a stone on a pond, delivering a glancing blow rather than a direct hit. The impact crater would have been elongated, energy dispersed, less material ejected. Still catastrophic, still an extinction event, but smaller, more survivable. 60 degrees was, in a sense, the worst possible angle. Steep enough to deliver the full kinetic energy directly to the crust, shallow enough to maximize the distribution of ejecta across the planet. If the asteroid had arrived 30 minutes earlier or later, Earth's rotation would have presented a different face. It might have hit the Pacific, the Indian Ocean, the Atlantic. Water impacts are less efficient at ejecting material into the stratosphere. The extinction would have been smaller. 30 minutes. That's the margin by which the dinosaurs lost and the mammals won. If you'd been able to delay the asteroid by the length of a sitcom episode, dinosaurs would likely still dominate terrestrial ecosystems. Mammals would remain small, nocturnal, marginal. And our lineage, primates, would never have gotten the opportunity to evolve. You exist because an asteroid hit at exactly the wrong angle at exactly the right time. But extinction, as violent as it is, only tells half the story. Because in the aftermath, life didn't just recover, it transformed. The Paleogene, the period immediately following the Cretaceous, was a world of ecological opportunity, empty niches, vacant real estate, and the survivors moved in. Flowering plants, angiosperms, had evolved during the Cretaceous, but they'd been subordinate to the gymnosperms, the conifers and cycads that dominated Mesozoic landscapes. Angiosperms had a trick, though. Seeds. Tough, resistant seeds that could survive fire, cold, and burial. After the impact, while gymnosperms struggled to recover from the loss of mature trees, angiosperms sprouted everywhere. Within 1 million years, they'd taken over. Today, roughly 90% of terrestrial plant species are angiosperms. The world you see outside your window, the grasses, the flowering trees, the crops that feed civilization, all of that is a consequence of an asteroid impact 66 million years ago. And with new plants came new plant eaters. Mammals, freed from the tyranny of dinosaurs, began to diversify. Not immediately. For the first few million years, they stayed small, rat-sized, possum-sized. But by 10 million years after the impact, mammals the size of ponies were walking around. By 15 million years post-impact, there were mammalian megafauna. And by 30 million years post-impact, the ancestors of horses, whales, elephants, primates, all the major mammalian lineages were established. Birds, technically dinosaurs, theropod dinosaurs, also diversified. Some became large flightless predators. Terror birds, standing 3 meters tall with beaks that could crack skulls. Others remained small, agile, filling ecological roles vacated by pterosaurs. The skies, once dominated by leathery winged reptiles, became the domain of feathered flyers. In the oceans, the extinction of mosasaurs and plesiosaurs opened up predatory niches. Sharks, which had survived the impact relatively well, expanded. Teleost fish, bony fish, radiated into countless forms. And mammals, some of them, returned to the water. The ancestors of whales, dolphins, seals, sea lions, manatees, all went back into the oceans within 10 million years of the impact, exploiting resources that marine reptiles had monopolized for 150 million years. The Mesozoic had been the age of reptiles. The Cenozoic became the age of mammals, not because mammals were superior, but because the reptiles that had been superior were dead. And the small, scrappy, opportunistic mammals were in the right place at the right time, with the right adaptations to exploit an empty world. Chance? Luck? A cosmic accident? That's the difference between dominance and extinction. And it's happened more than once. 445 million years ago, Earth experienced another mass extinction, the Ordovician-Silurian event, second only to the Permian-Triassic in severity. 85% of marine species gone. This was before land plants, before terrestrial animals. Life was almost entirely aquatic, and most of it died. The extinction happened in 2 pulses. First, a sudden onset of glaciation. Ice sheets spread from the supercontinent Gondwana at the South Pole, covering much of the southern hemisphere. Sea levels dropped as water was locked into ice. Marine organisms, adapted to warm tropical waters, froze. Entire ecosystems along continental shelves were left high and dry as the seas retreated. That was Pulse 1. Then, a few 100,000 years later, the ice melted. Rapidly, sea levels rose. But the warming didn't bring relief. Instead, it triggered widespread anoxia, oxygen depletion in the oceans. Organic matter, frozen and preserved during the glaciation, thawed and began to decompose, consuming oxygen faster than it could be replenished. Shallow seas became dead zones. Organisms that had survived the freezing suffocated in the warming. That was Pulse 2. For decades, geologists have tried to explain this extinction with terrestrial causes. Perhaps the evolution of land plants, just beginning in the late Ordovician, drew down atmospheric carbon dioxide, triggering a cooling. Perhaps volcanic activity decreased, reducing CO2 replenishment. Perhaps mountain building increased weathering rates, pulling carbon out of the air. All plausible, none entirely satisfactory. The onset was too sudden, the scale too large. Something was missing. Then, in the early 2000s, researchers started proposing something more exotic: a gamma-ray burst. Here's how a gamma-ray burst works. When the most massive stars, dozens of times the mass of the Sun, reach the end of their lives, they don't go gently. They collapse. Their cores implode into black holes or neutron stars, and in the process, they release more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. That energy doesn't radiate evenly. It's focused into twin jets, beams of gamma rays traveling at nearly the speed of light, funneled by magnetic fields into cones perhaps 1 to 2 degrees wide. If you're anywhere near one of those beams, you die. If you're a planet, your atmosphere dies. Because gamma rays are energetic enough to split molecular bonds. Ozone, O3, that fragile molecule that shields Earth's surface from ultraviolet radiation, doesn't stand a chance. A gamma ray burst from within about 6,000 light-years, pointed directly at Earth, would strip the ozone layer in seconds. And without ozone, ultraviolet radiation from the Sun, previously blocked, reaches the surface at full intensity. UV radiation is lethal. It damages DNA directly. At high enough doses, it kills cells outright. Organisms living on land or in shallow water where UV penetrates die, slowly, from radiation burns, from cancer, from cellular breakdown. Organisms in deeper water shielded by meters of H2O survive. The pattern of extinction in the Ordovician fits. Surface-dwelling organisms suffered more than deep water species. Planktonic life forms that floated in the upper ocean, exposed to light, died in massive numbers. Bottom dwellers living in darker, deeper environments fared better. That's consistent with a sudden, catastrophic increase in UV radiation. But a gamma-ray burst doesn't just kill with light. It also alters atmospheric chemistry. Gamma rays hitting the upper atmosphere ionize nitrogen and oxygen. Free nitrogen and oxygen atoms combine to form nitrogen dioxide, NO2. Nitrogen dioxide is a reddish-brown gas. It's also an aerosol. It lingers in the stratosphere for years, reflecting sunlight back into space, cooling the planet. If a gamma-ray burst hit the Ordovician Earth, the first effect would have been ozone destruction and UV sterilization. The second would have been atmospheric darkening and cooling. Within years, perhaps decades, the planet would have plunged into a glaciation. Ice sheets would have spread, exactly as the geological record shows. And then there's the third effect. Nitrogen dioxide eventually rains down to the surface. When it does, it delivers bioavailable nitrates, fertilizer. Phytoplankton, the base of the marine food web, bloom. Productivity spikes. And when those blooms die, they sink, decompose, and consume oxygen, creating anoxia, exactly as the second pulse of the extinction shows. A gamma-ray burst explains everything. The sudden onset, the two-phase nature, the selectivity of the victims. It's elegant, almost too elegant. The problem is, there's no way to prove it. Gamma rays don't leave fossils. They don't deposit iridium layers. They don't create impact craters. The only evidence would be isotopic anomalies in the rock record, traces of unusual nitrogen or beryllium isotopes created by the radiation. Researchers have looked. The data is inconclusive, so we're left with a hypothesis that fits the facts but can't be confirmed, unless it happens again. And statistically, it will. Gamma-ray bursts occur roughly 2 per billion years in a galaxy the size of the Milky Way. Earth is 4.5 billion years old. If one happened in the Ordovician 445 million years ago, we're overdue for another. When it happens, we won't see it coming. Gamma rays travel at the speed of light. There's no advance warning, no time to prepare. The first indication will be satellites failing, radiation detectors maxing out, the ionosphere rippling, and by then, the damage is already done. Within hours, the ozone layer begins to break down. Within days, UV levels at the surface start to climb. Within weeks, ecosystems begin to collapse. Could humanity survive a gamma-ray burst? Probably. We're clever. We'd move underground into shielded habitats. We'd wear protective suits. We'd adapt. But agriculture wouldn't survive. Crops exposed to the sky would wither under the UV. Livestock would die. Supply chains would collapse. Civilization, built on the assumption of a stable, habitable surface, would fracture. And if the burst was close enough, intense enough, even underground wouldn't help. A direct hit from a gamma-ray burst within 1,000 light-years would deliver enough radiation to penetrate tens of meters of rock. Nothing on the surface, nothing in the shallow subsurface would survive. Earth would be sterilized, not completely. Deep ocean vents, kilometers below the surface, would be fine. Microbes living in crustal rocks, insulated by kilometers of stone, would endure. But complex life that depends on the surface and the sun, would be gone. We exist in a shooting gallery. Every few 100 million years, the universe points a gun at us. Usually, it misses. Sometimes, it doesn't. And there's nothing we can do but hope the odds stay in our favor. But cosmic violence isn't the only way the universe shapes life. Sometimes, the influence is more subtle, more fundamental, written not into the fossil record, but into the very laws that govern how organisms can exist. Consider the color green. You see it everywhere. Grass, leaves, algae, forests covering continents, the dominant color of life on Earth. We take it for granted. But green is not inevitable. Green is a choice, an evolutionary choice, and it's a choice that was made for us by the star we happen to orbit. Plants are green because of chlorophyll, the molecule that captures light energy and converts it into chemical energy through photosynthesis. Chlorophyll absorbs light most efficiently in the red and blue portions of the visible spectrum. It reflects green light. That's why we see plants as green. They're literally rejecting that wavelength, bouncing it back to our eyes because it's not useful for their biochemistry. But why red and blue? Why not green? The answer lies 43 light-minutes away in the core of the Sun. Our Sun is a G-type main sequence star, what astronomers call a yellow dwarf. Its surface temperature is roughly 5,700 degrees Celsius. At that temperature, thermal radiation peaks in the yellow-green portion of the spectrum. The Sun produces light across the entire visible range, from red to violet. But the peak output, the wavelength where the most energy is concentrated, is yellow-green. You'd think plants would want to absorb that peak wavelength, maximize energy intake, but they don't. And the reason has to do with overheating and efficiency. If chlorophyll absorbed green light as well as red and blue, plants would absorb too much energy. Leaves would heat up. Water would evaporate faster. The plant would need more cooling mechanisms, more water, more metabolic overhead. By reflecting green, plants reject the peak of the solar spectrum, avoiding overheating while still capturing enough energy from the red and blue bands to power photosynthesis. It's a compromise, and it works, on Earth, around our Sun. But travel to a planet orbiting a different type of star, and the rules change. Red dwarfs, M-type stars, are the most common stars in the galaxy. They're smaller than the Sun, cooler with surface temperatures around 3,000 degrees Celsius. Their light is dim, reddish, concentrated in the infrared and deep red portions of the spectrum. The habitable zones around red dwarfs are close in, maybe 10 to 20 million kilometers, because the star is so dim. And on a planet in that habitable zone, photosynthesis would look nothing like it does here. To capture enough energy from a red dwarf's feeble light, photosynthetic organisms would need to absorb everything, especially the infrared. They wouldn't be green. They'd be black, dark blue, deep purple, colors that absorb as much of the available light as possible. And forests on such a planet, if they existed, would be dark, alien, unsettling to human eyes. A landscape of black trees under a dim red sun. On the other end of the spectrum, consider a planet orbiting an A-type star, a blue giant. Surface temperature 10,000 degrees Celsius. Light concentrated in the blue and ultraviolet. Brighter than the Sun, with a habitable zone farther out, maybe 2 to 3 times Earth's distance from the Sun. Photosynthesis on such a world would favor pigments that absorb blue and UV light. To avoid damage from the intense high-energy radiation, organisms might reflect blue, appearing yellow, orange, or red to our eyes. Or they might develop reflective, mirror-like surfaces, bouncing away the harmful UV entirely. The color of life is a function of the color of the star, and the color of the star is a function of its mass, which is a function of the amount of gas that collapsed to form it, which is a function of the density fluctuations in the molecular cloud that gave birth to it, which is a function of the turbulence and shock waves from previous generations of stars dying nearby. Chain of causation stretching back billions of years, across light years, determining whether the forests on your planet are green, black, or red. Every leaf you've ever seen is green because of a star that formed 4.5 billion years ago from a specific patch of gas in a specific region of the galaxy. Change any of those variables, and the forests change color. Or don't exist at all. But stellar type doesn't just affect photosynthesis. It affects the entire rhythm of life. Day length, night length, seasonal variation, all governed by orbital mechanics and planetary spin, which are themselves influenced by formation history and gravitational interactions. Earth rotates once every 24 hours. That's not a constant. When the planet first formed, the day was about 6 hours long. Tidal forces from the moon have been slowing Earth's rotation ever since, at a rate of about 2 milliseconds per century. In the deep past, days were shorter. In the far future, they'll be longer. Life adapts to the rhythm it's given. Circadian rhythms, internal biological clocks synchronized to the day-night cycle. Nearly every organism on Earth has one. Plants open and close their flowers on a schedule. Animals sleep and wake. Metabolism ramps up and down. Hormones fluctuate. all timed to the 24-hour day. Disrupt that rhythm, jet lag, shift work, and health suffers. The circadian clock is fundamental to biology, but on a planet with a 10-hour day, life would be different. Faster metabolisms, shorter sleep cycles, more frequent feeding, or perhaps no distinction between day and night activities at all, with organisms active continuously and relying on internal cues rather than external light. On a planet with a 40-hour day, the opposite. Long periods of activity followed by long dormancy. Hibernation-like states might be common even in tropical regions. And then there are tidally locked planets. Worlds where one hemisphere always faces the star, the other always faces away. No day-night cycle. Permanent day on one side, permanent night on the other. This is the fate of most planets orbiting red dwarfs, because the tidal forces are stronger when the habitable zone is close to the star. On a tidally locked world, the day side is scorched. Constant sunlight. No night to cool down. Temperatures soar. Hurricanes rage at the substellar point, where the sun hangs directly overhead forever. The night side is frozen. No sunlight ever. Temperatures plummet. Ice kilometers thick covers the surface. Life, if it exists, would be restricted to the terminator, the narrow band between day and night, where the sun sits perpetually on the horizon. A ring of eternal twilight encircling the planet. Temperatures moderate. Liquid water possible. And in that thin habitable zone, competition would be fierce. Limited space. Limited resources. Evolution would be brutal. Organisms packed into a sliver of habitability, fighting for every scrap. Some researchers think tidally locked planets could have another habitable region, the night side. Not on the surface, where everything is frozen, but underground. Geothermal heat from the planet's interior could melt subsurface ice, creating aquifers, cavern systems, hydrothermal ecosystems. Life without sunlight. Chemosynthetic organisms, like those around Earth's deep ocean vents, using chemical energy from rock-water interactions. A hidden biosphere, thriving in the dark, completely unaware of the star that defines the surface world. And if intelligent life evolved in such an environment, it would have no concept of astronomy. No sun, no stars, no sky. Just rock, water, and heat. Their cosmology would be entirely different. No reason to think the universe extends beyond the cavern walls. And if they eventually tunneled to the surface and discovered the day side, the night side, the terminator, the sky full of stars, it would be as shocking to them as discovering alien life is to us. Your environment shapes your understanding of reality, and your environment is shaped by cosmic factors you have no control over. The type of star, the distance from it, the rotation rate of your planet, the presence or absence of a large moon, all accidents of formation. Speaking of the moon, let's talk about what would happen if it wasn't there. The moon is enormous. Relative to Earth, it's the largest moon in the solar system. Ganymede and Titan are bigger in absolute terms, but compared to their parent planets, Jupiter and Saturn, they're tiny. The moon is 1/4 the diameter of Earth. It's less than 400,000 kilometers away. Gravitationally, it's a significant presence. And that presence has shaped life in ways that aren't immediately obvious. The most visible effect is tides. The moon's gravity pulls on Earth's oceans, creating two tidal bulges, one facing the moon, one on the opposite side. As Earth rotates beneath these bulges, coastlines experience high and low tides roughly twice a day. The range varies depending on geography, lunar phase, and other factors. But in some places, the difference between high and low tide can exceed 15 meters. Tidal zones, the regions of coastline submerged at high tide and exposed at low tide, are among the most biologically productive ecosystems on the planet. Organisms living there must tolerate both aquatic and terrestrial conditions. They're underwater half the time, exposed to air the other half. It's a harsh environment, but it's also an opportunity. Many evolutionary biologists think the tidal zone was the gateway to land. 400 million years ago in the Devonian, fish began to venture into shallow water. Some of them, lobe-finned fish, had muscular fins that could support weight. When tides receded and pools evaporated, these fish could use their fins to crawl to deeper water. Those that survived developed better air-breathing adaptations, stronger limbs, more tolerance for desiccation. Over millions of years, they became amphibians. And from amphibians came reptiles, mammals, birds, everything terrestrial. Without the moon, tides would still exist. Solar tides caused by the sun's gravity would remain, but they'd be much weaker. High tide might differ from low tide by half a meter instead of several meters. The intertidal zone would be smaller, less selective pressure, less evolutionary drive to adapt to both water and air. Would fish have colonized land without the moon? Eventually, probably. But it would have taken longer, tens of millions of years longer. And the trajectory of evolution would have been different. The moon also stabilizes Earth's axial tilt. Right now, Earth's rotational axis is tilted 23.5 degrees relative to the plane of its orbit around the Sun. That tilt is what gives us seasons. When the northern hemisphere is tilted toward the Sun, it's summer in the north, winter in the south. 6 months later, the tilt points the southern hemisphere toward the Sun, reversing the seasons. Over tens of thousands of years, Earth's axial tilt varies slightly, between about 22 and 24.5 degrees. That's a small variation, stable, predictable, and the reason it's stable is the moon. The moon's gravitational pull on Earth's equatorial bulge acts like a gyroscope, resisting changes to the tilt. Without the moon, Earth's axis would wobble chaotically. We know this because we can see it happening on Mars. Mars has 2 moons, Phobos and Deimos, but they're tiny, barely large enough to be round. They exert almost no gravitational stabilization. As a result, Mars's axial tilt has varied wildly over its history. Right now, it's about 25 degrees, similar to Earth's. But orbital models show that over tens of millions of years, it swung from near 0 degrees, essentially no tilt, to over 80 degrees, almost lying on its side. When Mars's tilt is low, the poles receive little sunlight year-round. Ice accumulates. The equator becomes the warmest region, and any remaining water or ice migrates there. When the tilt is high, the poles experience extreme seasons. 6-month-long days in summer, where the sun never sets and temperatures soar. 6-month-long nights in winter, where the sun never rises and everything freezes. Ice at the poles sublimates. Carbon dioxide from the polar caps enters the atmosphere. Atmospheric pressure increases. Then the tilt shifts again, and the process reverses. It's chaos. Climate swinging wildly over timescales of millions of years. Any life trying to gain a foothold on Mars would be repeatedly hammered by these oscillations. Just as organisms adapted to one climate regime, the axis would shift and conditions would change entirely. Some researchers think this instability is one reason Mars, despite being in the habitable zone early in its history, never developed a complex biosphere. Earth, by contrast, has enjoyed 4.5 billion years of relative climatic stability. Yes, there have been ice ages, greenhouse periods, snowball Earth events, but the axial tilt has remained within a narrow range. Seasons have remained predictable, and that predictability has allowed life to adapt, specialize, and diversify without constantly being reset by chaotic climate swings. All because of the Moon, which exists because 4.5 billion years ago, a Mars-sized protoplanet named Theia, traveling in a slightly eccentric orbit, happened to collide with the early Earth at precisely the right angle and velocity to blast enough material into orbit to coalesce into a large satellite. If Theia had been 10% smaller, the collision wouldn't have ejected enough material. If it had been 10% larger, Earth might have been destroyed entirely. If the angle had been different, more direct, the energy would have pulverized both bodies into fragments too small to recoalesce. If the angle had been too shallow, Theia might have glanced off, leaving Earth moonless and scarred. The margin for creating the Moon was narrow, and without the Moon, Earth's axis would wobble, tides would be weak, and the evolutionary path that led to terrestrial vertebrates, mammals, and eventually humans would have been very different. You exist because of a collision that happened before the first oceans formed, before the first continents, before the first single-celled organism. Your existence depended on that collision going exactly right, and the odds of it going exactly right were astronomically small. Luck, again. The dice rolled, and improbably, we're here. But let's go deeper. Let's talk about the stuff you're made of, because even the atoms in your body required cosmic accidents to exist. Hydrogen is easy. It formed in the Big Bang 20 minutes after time began. Helium, too. Trace amounts of lithium and beryllium. But that's where primordial nucleosynthesis stopped. The universe, in its first few 100,000 years, consisted almost entirely of hydrogen and helium gas. No carbon, no nitrogen, no oxygen, none of the elements necessary for chemistry, for rocks, for life. To make those elements, you need stars. Specifically, you need stars to die. Inside a star's core, hydrogen fuses into helium, releasing energy. That's how stars shine. As the star ages and exhausts its hydrogen, it starts fusing helium into heavier elements: carbon, oxygen, neon, magnesium, silicon, iron. Each fusion step requires higher temperatures and pressures. Only the most massive stars, those with at least 8 times the Sun's mass, can fuse elements all the way to iron. And then they explode. When a massive star runs out of fuel, its core collapses. In less than a second, the core implodes from the size of Earth to the size of a city. Protons and electrons crush together, forming neutrons, a neutron star. The collapse releases gravitational energy, a supernova, an explosion so bright it can briefly outshine an entire galaxy. And in that explosion, elements heavier than iron are created: gold, silver, uranium, platinum, forged in seconds, scattered into space. The gas and dust from that explosion, enriched with heavy elements, eventually collapses under its own gravity, forming new stars and planets. And those planets, built from the ashes of dead stars, have the raw material for chemistry, for life. Our solar system formed 4.5 billion years ago from a molecular cloud that had been enriched by multiple generations of stellar death. The Sun's metallicity, the fraction of elements heavier than helium, is about 1.3%. That doesn't sound like much, but it's enough. Enough to build rocky planets, enough to create an atmosphere, enough to allow biochemistry. If the solar system had formed earlier in the galaxy's history, when fewer stars had died and metallicity was lower, there might not have been enough heavy elements to build Earth. Or Earth might have been smaller, with a thinner crust, a weaker magnetic field, less volcanic activity. Plate tectonics might not have started. Without plate tectonics, carbon cycling would be disrupted, climate would destabilize, and the planet might end up like Venus, a runaway greenhouse. If the solar system had formed in a different part of the galaxy, away from the spiral arms where star formation is concentrated, metallicity might also be lower. The galactic halo, the outer regions, the space between spiral arms, these areas have fewer heavy elements. Planets there, if they exist, would be gas poor, metal poor, hostile to life as we know it. We're here because the Sun formed in the right place at the right time from gas that had been enriched by the right number of previous stellar generations. And that's not something you can control. It's geography, cosmic geography. But it's not just the presence of heavy elements that matters. It's the specific distribution, the ratios. Carbon is essential for organic chemistry. Oxygen is essential for water and respiration. Nitrogen is essential for amino acids and DNA. Phosphorus is essential for energy transfer and genetic material. Sulfur is essential for some proteins. Life, as we know it, requires all of these in roughly the right proportions. And those proportions are set by stellar processes. Carbon is made in helium-burning stars. Nitrogen is made in the CNO cycle, a catalytic fusion process that occurs in stars more massive than the Sun. Oxygen is made in later stages of stellar evolution. Phosphorus and sulfur are made in supernovae. Each element has its own nucleosynthetic pathway, its own origin story. If the galaxy's star formation history had been different, if massive stars had been more or less common, if supernovae had been more or less frequent, the elemental ratios would be different. A universe with less carbon and more oxygen might favor silicon-based chemistry. A universe with more nitrogen might favor different amino acid structures. A universe with less phosphorus might make DNA prohibitively expensive metabolically, forcing life to use alternative information storage molecules. We're built from the elements that happen to be abundant in this universe at this time. And those elements are abundant because of the specific history of star formation and death in our galaxy. Change that history, and you change the chemistry of life, possibly beyond recognition. But even with the right elements, you still need them to assemble into useful molecules. And that requires energy. Specifically, it requires the right kind of energy delivered in the right way. In 1953, a graduate student named Stanley Miller and his advisor, Harold Urey, conducted what would become one of the most famous experiments in the history of biology. They wanted to test whether organic molecules, the building blocks of life, could form spontaneously under the conditions thought to exist on the early Earth. They built a simple apparatus, a sealed glass system containing water, methane, ammonia, and hydrogen, gases that were believed at the time to represent the primordial atmosphere. They heated the water to create vapor, circulated it through the gas mixture, and then introduced an energy source. Electric sparks, simulating lightning. The experiment ran for a week. When Miller analyzed the resulting liquid, he found amino acids, glycine, alanine, aspartic acid, the basic components of proteins, organic molecules created from inorganic precursors using nothing but simple gases and electricity. It was a revelation. Life's building blocks weren't special. They could form naturally given the right conditions and an energy source. Since then, variations of the Miller-Urey experiment have been conducted hundreds of times, with different gas mixtures, different energy sources, different conditions. And the result is always the same. Organic molecules form easily, too easily almost. Amino acids, sugars, nucleotide bases, lipids, all the components of biochemistry, assembling themselves from simple chemistry when you add energy. But here's the interesting part. The energy source matters. In the original Miller-Urey experiment, it was electricity, lightning. But lightning isn't the only game in town. Ultraviolet radiation works. Heat works. Shockwaves from meteor impacts work. And all of these energy sources have one thing in common. They come from outside the system, from the sun, from cosmic rays, from asteroids, from space. The early Earth was bombarded by energy from every direction. The sun, younger and more active, produced intense UV radiation. The atmosphere, lacking oxygen and ozone, didn't filter it out. UV light penetrated deep, driving chemical reactions in the oceans and atmosphere. Cosmic rays, high-energy particles from supernovae and other stellar explosions, slammed into the upper atmosphere, ionizing molecules, creating reactive species, initiating chemistry. And then there were the impacts. The late heavy bombardment, a period roughly 4 billion years ago when the inner solar system was pelted by asteroids and comets, delivered both raw material and energy. Each impact vaporized rock, created shock waves, generated heat. In the aftermath, the atmosphere would have been filled with reactive gases, ready to combine into more complex molecules. The entire planet was a chemical reactor. Energy in, organic molecules out. And the energy came from space. Without it, without the sun's UV, without cosmic rays, without impacts, the chemistry would have stalled. The building blocks of life wouldn't have formed. Or they would have formed so slowly that the window of opportunity might have closed before life could get started. But here's something even more interesting. Organic molecules don't just form on planets. They form in space. In the 1960s and 70s, as radio telescopes improved, astronomers started detecting unexpected signals from interstellar space. Not from stars, from the stuff between stars. Molecular clouds, giant clouds of gas and dust, the birthplaces of new stars. And those clouds weren't just hydrogen and helium. They contained molecules, complex molecules, formaldehyde, methanol, ethanol, acetone, amino acids, sugars. Over 200 different organic molecules have been detected in space so far. Some of them are simple, 2 or 3 atoms. Others are large, complex, with dozens of atoms. And they're everywhere. In star-forming regions, in planetary nebulae, in the atmospheres of comets, even in meteorites that have fallen to Earth. The Murchison meteorite, which fell in Australia in 1969, contained over 90 different amino acids. Only 19 of those are used by life on Earth. The rest are what chemists call non-biological. They don't appear in proteins or enzymes, but they're still amino acids, still organic, still complex, and they formed in space, not on a planet. This changes the equation. Life's building blocks aren't just created on planetary surfaces. They're created in the cosmos, in molecular clouds, on asteroids, in comets. And they're delivered to planets during formation, during bombardment, continuously, for billions of years. The early Earth didn't have to synthesize all its organic molecules from scratch. A significant fraction was imported, pre-made, ready to use. Some researchers estimate that the early Earth received between 10 to the power of 16 and 10 to the power of 18 kilograms of organic material from space over the first few 100 million years. That's between 10 million and 1 billion kilograms. Enough to coat the planet's surface in a layer of organic goo several meters thick. Obviously, it didn't accumulate that way. Most of it was destroyed by impacts, by UV radiation, by oxidation. But some of it survived, enough to seed the oceans, the lakes, the tidal pools, enough to give chemistry a head start. And if organic molecules are common in space, that has profound implications for the prevalence of life in the universe. Because it means one of the hardest steps, creating the building blocks, isn't actually that hard. It happens naturally, everywhere, in every molecular cloud, in every protoplanetary disk, on every asteroid. If you have carbon, hydrogen, oxygen, nitrogen, and an energy source, you get organic molecules, automatically. The question then isn't whether the ingredients for life are available. They are. The question is whether those ingredients can assemble into something that reproduces, evolves, and complexifies. And that, we don't know, because we only have one example, us. But even the example of us, of Earth, reveals something subtle, something about the way organic molecules are structured, a quirk of chemistry that points back to cosmic influences. Many organic molecules are chiral. They exist in two forms, mirror images of each other, like your left and right hands. They have the same components, the same atoms, the same bonds, but they're oriented differently. One is left-handed, the other is right-handed. And you can't superimpose them. If you try to fit a left-handed molecule into a right-handed slot, it doesn't work. In non-biological chemistry, chiral molecules form in equal amounts, 50% left-handed, 50% right-handed. There's no preference, no reason for one to dominate over the other. They're energetically equivalent, chemically identical in most reactions. But biology is different. Life on Earth uses exclusively left-handed amino acids. Every protein in every organism, from bacteria to blue whales, is built from L amino acids, never D amino acids. The mirror image forms exist. You can synthesize them in a lab, but biology doesn't use them, and it's the same with sugars. Life uses exclusively right-handed sugars, D-glucose, D-ribose, D-deoxyribose, the sugar in DNA. The left-handed forms exist, but biology rejects them. Why? For over a century, this was a mystery. There's no obvious reason why life should prefer one-handedness over the other. Once the preference was established, sure, it makes sense to stick with it. Enzymes are stereospecific. A right-handed enzyme won't work on a left-handed substrate. If early life happened to start with L amino acids, all subsequent life would be stuck with that choice. But why did it start with L amino acids? Why not D? Or why not a mixture? Random chance was the standard explanation for decades. Life started with L amino acids because the first self-replicating molecule happened to use them. Flip a coin. It came up L. If we rewound the tape and started life over, it might come up D. But in the last 20 years, evidence has emerged suggesting it's not random. There's a bias. a subtle preference for one-handedness over the other, built into the universe itself. And that bias comes from space, circularly polarized light. Ordinary light waves oscillate in all directions perpendicular to the direction of travel. Circularly polarized light oscillates in a spiral, either clockwise or counterclockwise. And chiral molecules interact differently with circularly polarized light, depending on their handedness. Left-handed light preferentially destroys right-handed molecules. Right-handed light preferentially destroys left-handed molecules. Most light sources, like the sun, produce unpolarized light. No net preference. But some astrophysical environments produce circularly polarized light. Neutron stars, regions near black holes, supernovae, areas where magnetic fields are extremely strong and aligned with the light's direction of travel. In these regions, light can be up to 20% circularly polarized. If organic molecules in a molecular cloud are exposed to circularly polarized UV radiation for millions of years, one-handedness will be destroyed faster than the other. Not completely, but enough to create an imbalance. Instead of 50-50, you might get 55% of one-handedness and 45% of the other. That's a small difference, but it's enough. Because once you have even a slight excess of one form, autocatalytic processes can amplify it. If L-amino acids are slightly more common, reactions that favor L-amino acids will be slightly more efficient. Products of those reactions will preferentially use L-amino acids, further increasing the imbalance. Over time, the minority-handedness gets squeezed out, not by design, by statistics. And if this happens in space, if the organic molecules delivered to planets already have a handedness bias, then life starting from those molecules would inherit that bias. It wouldn't be a coin flip, it would be predetermined. By radiation from neutron stars, billions of years ago. There's some evidence for this. Meteorites that contain amino acids don't show a 50-50 split. Some show up to 15% excess of L-amino acids. Not as extreme as biology's 100% preference, but enough to suggest that the bias existed before life. If this is true, if the handedness of life was determined by astrophysical processes in the molecular cloud that formed the solar system, then every organism on Earth, every protein, every enzyme, every strand of DNA carries a signature of stellar death and magnetic fields and circularly polarized light from before the sun was born. You're left-handed at the molecular level because a neutron star somewhere in the Milky Way 5 billion years ago emitted circularly polarized ultraviolet radiation into a gas cloud. That's the level of cosmic influence we're talking about. Not just shaping ecosystems, not just delivering asteroids, shaping the chirality of biochemistry. Everything about you, from the color of the plants you eat to the structure of the molecules in your cells, was decided by processes that occurred light years away, millions or billions of years before you were born. But let's take one more step back. Let's ask the most fundamental question. Why is there anything at all? Why are there atoms? Why is there matter? Why is the universe capable of making stars, planets, and life? Because it almost wasn't. In the first trillionth of a second after the Big Bang, the universe was a roiling soup of energy. No particles, no atoms, just energy, condensing out of the initial singularity, expanding, cooling. As it cooled, energy converted into matter, particle-antiparticle pairs, quarks and antiquarks, electrons and positrons. For every particle, an antiparticle. And when a particle meets its antiparticle, they annihilate, convert back into energy. In a perfectly symmetric universe, every particle would have an antiparticle, and they'd all annihilate, leaving nothing but photons. No matter, no atoms, no chemistry, no possibility of complexity. The universe would be empty, photons spreading out forever into an expanding void. But that's not what happened. For reasons we still don't fully understand, there was a slight asymmetry. For every billion particle-antiparticle pairs, there was one extra particle. 1 in a billion. Almost everything annihilated. Particles and antiparticles destroyed each other in a blaze of gamma rays. But that 1 in a billion excess survived. And that excess is everything. Every atom in your body, every star, every planet, every galaxy, all of it came from that tiny imbalance in the first microsecond of the universe. We don't know why the imbalance existed. It's one of the great unsolved problems in physics. The standard model of particle physics predicts symmetry, equal amounts of matter and antimatter. But the universe clearly violated that symmetry. Something broke the balance. Some process, some interaction, some field tipped the scales by 1 part in a billion. If it hadn't, you wouldn't be here. There'd be no atoms, no chemistry, no stars. Just an empty universe filled with photons left over from the annihilation. This is what physicists call fine-tuning. The fundamental constants of the universe, the strength of forces, the masses of particles, the rate of expansion, all of them sit within narrow ranges that allow complexity to exist. Change any of them by a small amount, and stars don't form, or they burn out too quickly, or atoms don't bind, or the universe collapses back on itself before anything interesting happens. Some people find this unsettling. It feels like the universe was designed, calibrated, set up specifically to allow stars, planets, and life. But there's another explanation, the anthropic principle. We observe a universe capable of supporting life because if it wasn't capable of supporting life, we wouldn't be here to observe it. We're biased observers. We can only exist in a universe that permits our existence. If there are countless universes, a multiverse, each with different constants, different laws, then the vast majority would be sterile, empty. But a tiny fraction would, by chance, have constants that allow atoms, stars, planets, chemistry. And in those rare universes, life could emerge. And intelligent observers could look around and marvel at how finely tuned everything is, not realizing that they're only asking the question because they happen to live in one of the rare universes where it's possible to ask questions. It's survivorship bias on a cosmic scale. We're the lottery winners wondering why we're so lucky, not realizing that countless non-winners never got the chance to wonder anything. But whether it's design, luck, or anthropic selection, the result is the same. The universe you inhabit is capable of supporting you. Barely. Change one constant, one force strength, one particle mass, and it all falls apart. The strong nuclear force, which holds atomic nuclei together, is calibrated to allow carbon to form in stars. If it was slightly stronger, carbon wouldn't be stable. If it was slightly weaker, helium wouldn't fuse into carbon in the first place. No carbon, no organic chemistry, no life. The electromagnetic force, which governs chemical bonds, is calibrated to allow molecules to form. Stronger, and electrons would be bound too tightly to interact. Weaker, and atoms wouldn't bond. No molecules, no chemistry. The cosmological constant, the energy density of empty space, determines the expansion rate of the universe. Too high, and the universe expands so fast that matter never clumps into galaxies and stars. Too low, and the universe collapses before stars can form. The measured value is small, very small, but not zero. And if it were much different, we wouldn't be here. This is uncomfortable, it feels arbitrary, but it's also liberating, because it means the universe isn't hostile. It's not indifferent. It's not trying to kill you. It's simply capable of supporting you. And that capability, whether by design or by anthropic selection, is rare, precious, fragile. Every star you see in the night sky is possible because the strong force has the value it does. Every breath you take is possible because the electromagnetic force allows oxygen to bind to hemoglobin. Every thought you think is possible because carbon, nitrogen, and oxygen were synthesized in stars that exploded billions of years ago. You're not separate from the cosmos. You're a part of it. A temporary, improbable arrangement of atoms that the universe has assembled briefly to look back at itself and wonder why. And the wondering matters. Because we're the universe's way of knowing itself. The cosmos, unconscious and vast, has created, through billions of years of stellar alchemy and planetary evolution and biological complexity, something that can observe, understand, and question. Consciousness, intelligence, science. We're not outside observers looking at the universe. We're the universe looking at itself. Carl Sagan said it best. We are a way for the cosmos to know itself. Every discovery we make, every equation we solve, every star we catalogue is the universe examining its own structure. We are its self-awareness. And that makes the question of whether we're alone in the cosmos even more profound. Because if we are, if intelligence is so rare that we're the only instance of it in the observable universe, then we're the only way the cosmos has to know itself. And if we destroy ourselves through war or climate change or artificial intelligence gone wrong, we're not just ending humanity. We're ending the universe's self-awareness. For billions of light years in every direction, as far as we can see, we've detected no signal, no transmission, no techno-signature, no evidence of other civilizations. 60 years of searching, thousands of star systems examined. Nothing. That doesn't mean they're not out there. The galaxy is vast. We've barely scratched the surface. But it does mean they're not common. Not obvious. Not broadcasting at frequencies and power levels we can detect. Either they're very far away, or very quiet, or very rare, or we're first, or last, or alone. If we're alone, it's because a trillion things had to go right. The universe had to have the right constants. The galaxy had to form stars with the right metallicity. A molecular cloud had to collapse at the right time. A planet had to form at the right distance from a star of the right type. That planet had to be the right size, with the right atmosphere, the right magnetic field, the right amount of water. It had to be hit by an impactor at the right angle to form a large moon. It had to avoid close-range gamma-ray bursts for 4 billion years. It had to be bombarded by asteroids that delivered organic molecules without sterilizing the surface. And then, somehow, chemistry had to become biology. Every step is a filter, a barrier that most planets don't pass. And if Earth is the only planet that passed all of them, then we're it. The only consciousness in the cosmos, the only observers, the only way the universe knows itself. That's a terrifying responsibility, and a profound one. But even if we're not alone, even if there are a million other civilizations out there scattered across the galaxy, we still have a responsibility to ourselves, to the biosphere that created us, to the universe that made us possible. Because we're the product of cosmic chance, and cosmic chance can take away what it gave. Let's return to where we started. October 9th, 2022. The boat. The brightest gamma-ray burst ever recorded. 2 billion light-years away, a massive star collapsed, formed a black hole, and in its death throes, emitted a jet of gamma rays pointed almost directly at Earth. Almost. If the jet had been aimed 1 degree more precisely in our direction, the intensity would have been higher, not catastrophically higher. The distance was still enormous, but measurably higher. Enough to cause more atmospheric disruption. Enough to degrade the ozone layer by a few percent instead of a fraction of a percent. Enough that, had it been closer, the damage would have scaled accordingly. 6,000 light-years is the danger zone. Within that radius, a gamma-ray burst pointed at Earth would strip the ozone layer entirely. Lethal UV radiation would reach the surface within days. Photosynthetic organisms in the upper oceans would die within weeks. Land plants, less protected, would wither within months. Herbivores would starve. Ecosystems would collapse. Within a year, much of the biosphere would be gone, and we wouldn't see it coming. Gamma rays travel at the speed of light. The first indication would be satellites failing, instruments saturating, communications disrupting. And then, within hours, the ionosphere would begin to break down. Within days, UV levels would spike. By the time we understood what was happening, it would already be over. Could humanity survive? Underground, yes. We'd retreat to bunkers, tunnels, mines. We'd grow food under artificial lights. We'd recycle water and air. A remnant population, maybe a few million, could endure for decades, maybe centuries. But surface agriculture would fail. Supply chains would collapse. Billions would die. Not from the gamma rays directly, from starvation, from the cascading failure of civilization. And when we finally emerged, decades or centuries later, the world would be unrecognizable. Forests gone, grasslands barren, oceans filled with dead zones. The few species that survived, extremophiles, deep-sea organisms, burrowers, would inherit a sterilized planet. And it would take millions of years for the biosphere to recover. That's the scenario. That's what a close-range gamma-ray burst would do. And statistically, it's overdue. The Ordovician extinction 445 million years ago may have been caused by one. If the hypothesis is correct, that's the last time Earth took a direct hit. Which means we've gone 445 million years without another. Gamma-ray bursts occur roughly twice per billion years in a galaxy the size of the Milky Way. We're halfway through the expected interval. Of course, statistics don't work that way. Just because we're overdue doesn't mean it's imminent. It could happen tomorrow. It could happen in 100 million years. The universe doesn't keep a schedule, but the possibility is real. And it's not something we can prevent, or predict, or prepare for beyond basic resilience. All we can do is hope the dice keep rolling in our favor. And that's the uncomfortable truth about existence. We're here because the dice have so far rolled in our favor. Not just once, repeatedly, for billions of years. Every generation, every species, every individual. You're the product of an unbroken chain of survival stretching back 4 billion years. Every one of your ancestors survived long enough to reproduce. Every single one. No exceptions. That's 1 trillion consecutive dice rolls, all coming up favorable. And if any one of them had failed, you wouldn't exist. If a predator had caught your great-great-great-grandmother 1,000 generations ago, before she reproduced, you wouldn't exist. If a drought had killed your ancestor 10 million years ago, you wouldn't exist. If the asteroid 66 million years ago had missed Earth, dinosaurs would still dominate. Mammals would be nocturnal rat-sized creatures, and you wouldn't exist. Your existence is contingent, fragile, dependent on a chain of improbable events. And the chain is still extending. The dice are still rolling. And eventually, inevitably, they'll come up wrong. Not necessarily in your lifetime. Not necessarily in humanity's lifetime. But eventually. Because extinction is the rule, not the exception. 99.9% of all species that have ever lived are extinct. The average lifespan of a species is about 1 to 10 million years. Homo sapiens is roughly 300,000 years old. We're young. Evolutionarily, we're in the early phase. And while we're clever, while we've built civilization and technology and science, we're not exempt from the forces that killed everything else. We like to think we're different. That intelligence gives us an edge. That technology makes us invulnerable. But intelligence didn't save the Neanderthals. Technology didn't save the Romans, the Maya, the Easter Islanders. Civilizations collapse. Regularly, predictably. And when they do, populations crash, knowledge is lost, and survivors start over. We're playing a game with high stakes and no safety net. And the universe is the dealer. But here's the thing. Knowing that we're fragile, that we're contingent, that we're lucky, doesn't have to be paralyzing. It can be empowering. Because if we understand the forces that shaped us, the cosmic accidents that made us possible, we can start to make choices that aren't purely dependent on luck. We can't prevent gamma-ray bursts, but we can become a multi-planetary species, spreading the risk. If Earth is sterilized, colonies on Mars, the Moon, orbital habitats could preserve humanity. Not easily, not comfortably, but survivably. We can't prevent asteroid impacts, but we can detect them, track them, and with enough warning, deflect them. The DART mission, successfully completed in 2022, proved that kinetic impactors work. We can change an asteroid's trajectory. It's not science fiction, it's engineering. And if we invest in detection and deflection infrastructure, we can eliminate the asteroid threat entirely within a century. We can't prevent supervolcanoes, but we can prepare for them. Seed banks, underground agriculture, distributed infrastructure. If Yellowstone erupts tomorrow, civilization will be damaged. But it doesn't have to end. Not if we plan. And we can absolutely prevent the threats we're creating ourselves. Climate change, nuclear war, engineered pandemics, artificial intelligence run amok. These aren't cosmic dice rolls. These are choices. And unlike gamma-ray bursts or asteroids, we control them. The question is whether we're wise enough to make the right choices. Whether we can overcome short-term thinking, tribal instincts, and economic incentives that prioritize profit over survival. Whether we can look at the cosmic record, see how many species have gone extinct, how many civilizations have collapsed, and decide that we're going to be different. Because the universe doesn't care. The cosmos isn't rooting for us. It's not trying to kill us, but it's not trying to save us either. It's indifferent, neutral, It provided the conditions for our existence, but it's not going to protect us from our own stupidity. If we survive, it's because we choose to. If we thrive, it's because we're clever enough, wise enough, and cooperative enough to navigate the threats, both cosmic and self-inflicted. And if we fail, the universe will continue. Stars will shine, planets will orbit, and maybe, somewhere else, on some other world orbiting some other star, another species will look up at their sky and ask the same questions we're asking. Why are we here? Are we alone? What does it all mean? And maybe they'll find better answers than we did. But let's not concede defeat just yet, because despite the fragility, despite the contingency, despite the overwhelming odds against us, we're here. Against all probability, we exist. We're conscious. We can ask questions. We can seek answers. We can understand the universe. And that's not nothing. In fact, it might be everything. Think about what it took to create you. 13.8 billion years ago, the universe began. A singularity, infinite density, infinite temperature, and then expansion, cooling, energy converting to matter, particles forming, nuclei forming, atoms forming. For the first few 100 million years, it was just hydrogen and helium. No stars, no light, just gas spreading through the expanding void. Then, gravity. Tiny density fluctuations, quantum ripples from the first moments began to collapse under their own weight. Gas clouds condensed, heated, ignited. The first stars formed. Population 3 stars. Massive, short-lived, burning bright and dying young. And in their deaths, they forged the first heavy elements. Carbon, oxygen, iron, scattered into space. The next generation of stars formed from that enriched gas. Population 2 stars. Still massive, but with a bit of metal. And when they died, they enriched the gas further. More carbon, more oxygen, more iron, more of everything needed to build planets. Our Sun, a population 1 star, formed 4.5 billion years ago from a gas cloud that had been enriched by at least 10 to 20 previous generations of stellar death. It had enough heavy elements to form rocky planets, enough to create an atmosphere, enough to allow chemistry. Earth coalesced from that disk of gas and dust, slowly, over tens of millions of years. Dust grains stuck together, pebbles formed, boulders, planetesimals, protoplanets, collisions, mergers, growth, and eventually a planet roughly the size of Earth, orbiting at the right distance from the Sun to allow liquid water. But early Earth was hot, molten, bombarded by impacts, no atmosphere, no water. And then Theia, the Mars-sized impactor, the collision that blasted material into orbit, forming the Moon. The collision that nearly destroyed the planet, but instead created the stabilizing force that would allow life to persist. The late, heavy bombardment followed 4 billion years ago. Asteroids, comets, delivering water, delivering organic molecules, seeding the surface with the raw materials for life. And then, somehow, chemistry became biology. We don't know exactly how. Abiogenesis, the origin of life from non-life, is still one of the great unsolved problems in science. But it happened. Somewhere, in some tidal pool or hydrothermal vent or mineral-rich puddle, molecules started replicating, competing, evolving. And once that process began, it never stopped. 4 billion years of evolution, single cells, multicellular organisms, photosynthesis, oxygen, eukaryotes, animals, plants, fungi, extinctions, radiations, dinosaurs, mammals, primates, hominids, And finally, 300,000 years ago, Homo sapiens. You're the product of all of that. Every atom in your body was forged in a star. Every molecule was assembled by cosmic chemistry. Every gene was shaped by billions of years of natural selection. You're not separate from the universe. You're an expression of it. A temporary, localized increase in complexity. A pattern. A process. A way for the cosmos to know itself. And knowing that, knowing your origins, knowing the unimaginable sequence of events required to create you, what do you do with it? You could despair. You could look at the vastness of space, the age of the universe, the improbability of your existence, and feel insignificant, meaningless. A speck of dust on a speck of rock orbiting a speck of light in an incomprehensibly large and indifferent cosmos. Or you could marvel. You could recognize that you're the universe experiencing itself. That your consciousness, your ability to wonder and question and understand, is the most complex phenomenon we've ever discovered. That you're made of stardust, yes, but stardust that can think, that can create, that can love and dream and build and explore. You're not insignificant. You're rare, possibly unique, certainly precious. And the fact that your existence is contingent, that it required 1 billion lucky breaks, doesn't diminish it. It enhances it. Because it means you're here against the odds. You won the lottery. Not just you personally, but your species, your planet, your biosphere, all of it. The universe rolled the dice, and improbably, impossibly, here we are. So what do we do with that? We could waste it, squander it, destroy ourselves through ignorance, greed, tribalism. It wouldn't be unprecedented. Civilizations have collapsed before. Species have gone extinct. The universe would continue. It wouldn't mourn us. It would simply move on. Stars would shine. Planets would orbit. And maybe, billions of years from now, another planet around another star would give rise to another intelligent species. And they'd look up at their sky and wonder. Or we could rise to the challenge, recognize the fragility, accept the responsibility, make the choices that maximize our chances of survival. Not just survival, flourishing, expanding, becoming something greater than we are now. We could spread beyond Earth, make life multiplanetary, multi-stellar eventually. Remove the single point of failure. Ensure that no asteroid, no supervolcano, no gamma-ray burst, no self-inflicted catastrophe can end us entirely. We could preserve the biosphere, protect the ecosystems that created us, recognize that we're not separate from nature, we're part of it. And if we destroy it, we destroy ourselves. We could pursue knowledge, continue exploring, continue discovering, continue pushing the boundaries of what we understand. Because every discovery is the universe learning about itself. And the more we learn, the better equipped we are to navigate the challenges ahead. We could cooperate, overcome tribalism, recognize that borders, nations, ideologies, all of it is ephemeral, temporary, insignificant compared to the cosmic forces that shaped us. We're one species, on one planet, in one solar system, and if we're going to survive, we need to act like it. None of this is guaranteed. We could fail, probably will if history is any guide. But we could also succeed. We could be the species that breaks the pattern. That survives long enough to become something the universe has never seen before. A civilization that spans star systems, a consciousness that persists for millions, billions of years, a legacy that outlasts the sun. It's possible. Not easy, not guaranteed, but possible. And the first step is recognizing where we came from, understanding the cosmic forces that made us, acknowledging the luck, the accidents, the improbable chain of events that led to this moment. You exist because a star exploded 5 billion years ago, because an asteroid hit at the right angle 66 million years ago, because a gamma ray burst missed us 445 million years ago, because the moon formed from a perfect collision, because water was delivered by migrating planets, because organic molecules assembled in space and fell to Earth, because chemistry somehow became biology. Every breath you take is a consequence of cosmic roulette. Every thought you think is powered by mitochondria descended from bacteria that learned to breathe poison. Every choice you make is enabled by a brain shaped by millions of years of evolution in environments created by asteroid impacts, climate shifts, and stellar radiation. You're not separate from the cosmos. You're woven into it, built from it, shaped by it, and now, for the first time in 4 billion years, capable of understanding it. That's not insignificance. That's privilege. That's responsibility. That's meaning. The dice are still rolling. The universe is still indifferent. The threats are still real. But we're here, conscious, aware, capable of asking why, and maybe, just maybe, capable of ensuring that the answer isn't by accident, but by choice. The boat, that gamma ray burst in October 2022, was a reminder, a warning shot, a cosmic dice roll that came up favorable, barely. 2 billion light years was enough distance. 1 degree of misalignment was enough safety margin. We survived. Again. But the dice keep rolling, and eventually our luck will run out, unless we stop depending on luck. The universe gave us the tools: hydrogen from the Big Bang, heavy elements from dying stars, a planet in the habitable zone, a moon to stabilize it, water from asteroids, organic molecules from space, 4 billion years of evolution, intelligence, consciousness, science. What we do with those tools is up to us. We can sit here on this one fragile planet and wait for the next asteroid, the next gamma ray burst, the next self-inflicted catastrophe. And when it comes, we'll join the 99.9%, another extinct species, another failed experiment, another cosmic footnote. Or we can act. We can choose survival. We can spread. We can persist. We can become something the universe has never seen before. Not because we're special, but because we're conscious. And conscious beings can make choices. The cosmos doesn't care if we survive. But we do. And that's enough. You're stardust. You're the universe experiencing itself. You're the product of 13.8 billion years of cosmic evolution. You're here against impossible odds. Now, what are you going to do about it? The choice is yours. But make it quickly, because the dice are still rolling, and the universe isn't waiting. Thank you for watching. If you found this exploration meaningful, please consider subscribing and sharing it with someone who might appreciate the perspective. We're all in this together, navigating the cosmic lottery. The more of us who understand the stakes, the better our chances. Until next time, look up, remember where you came from, and choose wisely.